Welcome to today's lesson in precalculus on the continuity, end behavior, and limits. This is section 1.3. So to start off this lesson, we need to talk about what a continuous function is, because before we can get into limits, before we can get into any of this stuff, we have to understand what a continuous function is and what a discontinuous function is. So, a continuous function is a function that you can draw without lifting up your pencil. For example, if I have a function here and I do this, that is a continuous function. In every direction, I can draw it without lifting up my pencil. It still has to be a function, so it still should pass the vertical line test. But a continuous function, if I have to pick up my pencil at all, so if I am doing a function and I go along and then I pick up my pencil and I keep going, there's a spot there that I had to pick up my pencil. That is not continuous. Okay, another example would be if I had a function that does this kind of thing. Okay, it's not continuous because it's in two parts. This gets closer and closer to 0, this gets closer and closer to 0, but again, it's in two pieces. Okay, that is not continuous. A continuous function, you just can keep drawing with one pencil stroke. You don't have a hole in the middle of the function. You don't have a place where the ends don't meet. Now, a continuous function is very important so that we can understand the idea of a limit. Okay, so I'm going to draw an example here, and this is just a curve like this. Okay? Now, if I am trying to find the limit here, then I am going to choose x values that are closer and closer to this x. So I might pick an x value here. Okay? And I might pick an x value here. And these x values will give me certain y values. Okay? So if I call this x1, this would be f of x1. If I call this x2, then here would be f of x2. And I could pick x values on this side, like here, x3 and x4. Okay? These are also on my curve here, and they will give me unique y values. As I choose my x values so that I get closer and closer to this x that I'm after, this one right here, as I get closer and closer to this, my function values will get closer and closer to this f value right here that I'm after. Okay? That is a limit. A limit is simply, as I choose values closer and closer to a certain x, what will the function appear like it's going to go to? We'll be working with limits, some today, but a lot in the future. Limits are one of the basis of calculus. And so we'll be understanding and working with limits quite a bit. But this is a picture value of a limit. Okay, so as I am choosing a value, I'm going to get closer and closer and closer. Now, the way that you will see this written, okay, so this I'm going to call C now. The limit as x approaches C. Okay, that means x is getting closer and closer and closer and closer to that C value of f of x. So this function will equal L. And that's where this value right here would be my L. Okay, so this is simply stating in mathematical language what we're talking about here. As I choose x's that are closer and closer to a certain value, then the function values will get closer and closer and closer to a certain value. And that value would be L. Okay? And when we read this, we say the limit of f of x as x approaches C is L. I know, it's a huge sentence all in that one thing. I'll say it one more time. The limit of f of x as x approaches c is L. That is a whole sentence just in that little equation right there. Okay? Now, to understand continuous functions, it is easiest to look at what discontinuities could exist and what you would see as we deal with them. So I've got 3 different kinds of discontinuities that we'll be dealing with. The first one here is an infinite discontinuity. An infinite discontinuity means at least one of the ends are going to infinity. So I'm going to make my discontinuity right here, and I'm going to make this come down like this and go this way, and then I'll do the same on the other side. Okay? Do you see how both of these ends are heading toward infinity? Whether they go toward infinity in the same way or in the opposite direction, it doesn't matter. It means one of these are heading toward infinity. Okay? This means as x approaches my value here of c, I'm going to end up going to infinity, or I'm going to end up going to negative infinity. Now, often when you're seeing this, you're going to see something like 1 over x. Okay? Because as I get closer and closer to 0, in this case, if I get close to 0, I'm going to get a really big number. For example, when x is 1/2, I get 2. When x is 1/3, I get 3. When x is 1/4, I'd get 4. Think about that. Convince yourself of that. Consider as I put smaller and smaller numbers on the bottom, what my value is here. Play with it in your calculator if you need to. Okay, so that's an infinite discontinuity. At least one side will approach infinity. Okay, then we have a jump discontinuity. This often occurs when we have a piecewise function, something that we are defining from one piece to the next piece to the next piece. This is where, like at this value c, I have a circle there where it doesn't equal c, but it comes up like that. And then right here, it equals c, and it goes like that. That means as I'm going to c from the negative side, from the left, as I approach from this way, I'm going to reach this number. But as I approach from the right, I'm going to reach a different number. This is usually piecewise. Usually you'll have 2 different functions that are defining this at c. Okay? And then you have removable discontinuities. Okay? Removable discontinuities can happen with piecewise. It can also happen with fractions. Okay? So if I have a curve here that looks continuous, but if for some value here, it simply doesn't equal right there for this value c. That is called a removable discontinuity, because if I were to define c to equal this value, it would be gone. So that one I can remove if I need to, but the way that it's written, I have a discontinuity there. Well, it doesn't necessarily help if I know what's continuous and what is discontinuous without actually knowing how to test for it. Because if I can't test for continuity other than graphing, then I'm going to have a very hard time graphing some of these functions. So there is a test that we can use for continuity. So the continuity test, there are 3 statements that you must know, and each one of these, when taken together, will prove that it is continuous at a certain point. It does not mean that it's continuous everywhere. It means that at that point, it is continuous. So, first of all, test number 1, f of c is defined. Okay, that's to prove that it's not something like this, where here at c there is no function value. So here, f of c is not defined. Okay, so we need f of c to be defined. Okay, basically, I need to know that f of c exists. Okay, if it doesn't exist, I've got issues because I know instantly there's some sort of discontinuity. Don't necessarily know for sure it's this one, or if it's this one, or if it's this one, because here there is no f of c. Here there's no f of c. Here, if I made this one a circle instead of a dot, there would be no f of c. So f of c has to be defined. If it's not defined, I've got my first problem. The next thing, f of x has to approach the same value from each side of c. So basically, the limit of f of c exists. The limit of f of x as x approaches c. Okay? That means that from the left and from the right, they have to approach the same value. Okay? You'll see this notation in the future, and I may be using it later here. So basically, the limit of f of x as x approaches c, and then when I'm approaching from the left, from the negative side, so I start somewhere here on the lower side and I go towards c. So I put a little negative sign here. That means from the left has to equal the limit of f of x as x approaches c. Now, when I'm above c and I'm starting with a bigger number, I'm going to go down towards c. That means from the positive side. Okay, so from bigger and from smaller. These two have to equal. That's so that I don't come down like this into two different numbers. All right, the third test. The value that f of x approaches. So this one exists and this one exists. Then I need f of c has to equal has to equal the limit of f of x as x approaches c. They must be the same. So basically, I don't want something like this, where I get like this with a hole there, and then I get that filled down here. Okay? So here at c, f of c exists, and the limit exists, but the two are not the same, so I still have a discontinuity. All right, are you ready to play with this sum? Let's take a look here. We're going to work at these examples, testing to see if f of x is continuous at the point. So at x equals 0, so test number 1, I need to know, does f of 0 exist? Okay, so I plug 0 in. F of 0 equals 0 cubed equals 0. Yes. Okay, the limit of, this is test 2, the limit of f of x as x approaches 0. Okay? To do this, we have to use a table for right now. Later on, you'll learn how to find out how limits exist without tables. But just like when you were learning to graph, you started with tables and then learned the tricks. Well, here we start with tables and then you can learn the tricks. So, working here, I'm going to say here is 0. I'm going to pick some numbers bigger and some numbers smaller. And we're going to have to use a calculator. Should make this a little bit farther. So, something that is slightly larger, let's see, let's try, shall we do 3 or 4? In the book they do 3, and so I'll do 3. Something slightly larger than 0 would be a 0.1. Now, I need something between 0.1 and 0. So I'm going to say 0.01, and I'm going to push that 1. So this is like 10 cents and then 1 cent, and then I'm going to push it one more time, 0.001. This way, I can start figuring out what's going on and get close to 0. Okay? And then I also have to look at this side. And so I'm going to start over here. What is close to 0? Well, 0.9. Sorry, negative 0.1. Negative 0.1. Okay, now I want to get even closer to 0, so negative 0.01. This is like you owe somebody 10 cents, you owe somebody 1 cent, and then here you owe them 1/10 of a cent. 0.001. All right, now you get to pull out your calculators. I'm pulling out mine. Okay, this is the kind of calculator I told you it would be wise to get. Now, I am trying to plug in x cubed. So I'm going to go open parentheses, open parentheses, negative 0.1, close parentheses, cubed, equals. Okay, so this is negative. I'm going to change that. If you use this button right here, change that to decimal. So does it change again for me? Nope. Okay, I have mine set in scientific. There should be a way. I'd have to go in and change the settings on my calculator so that it gives me decimal form. But this is negative 0.001. I'm actually going to write it in the scientific notation so that we have a way to compare. Negative 1 times 10 to the negative 3. Okay, that means the decimal is going to be smaller. The decimal is going to move this way 3 places. All right, so now I can go in here and edit and add a 0. Enter. Okay, now it's 0.6. So negative 1 times 10 to the negative 6. All right. Now let's try and add one more 0 in there. And now it's to the negative 9. Negative 1 times 10 to the negative 9. As you can see, this is being pushed back. The 1 is being pushed smaller and smaller and smaller. So this limit is 0. Okay? Now let's look at the other side. Well, the only difference here is the negative sign. So I'm going to start here and I'm going to delete the negative sign, equals. Well, now it's 1 times 10 to the 9. And then you can go in here and delete a 0. And now then it's 1 times 10 to the 6. And then I can go in and delete another 0. And this is 10 to the 3. 1 times 10 to the 3. Oops, that's 103. I need that more of an exponent and less of a number. So as I'm going this direction, again, I'm getting smaller and smaller and smaller, so I'm going to 0. Because they're going the same from each direction, I can say that this limit of f of x as x approaches 0, which we also could write the limit of x cubed as x approaches 0, equals 0. Okay? Now, the last step, step 3, are these two equal? So then you say f of 0 equals 0, which is the same as the limit of f of x as x approaches c. Therefore, f of x is continuous. There's a u in there. At x equals 0. So I was able to conclude this. All right, let's try another one. This is another kind of example you may run into where I have two pieces. Okay, so for part of the time I'm going to have to deal with this one, And for part of the time, I'm going to have to deal with this one. Again, I'm doing x's at 0. So, step 1. Does f of 0 exist? Okay, so f of 0, I look up here in the definition. If it equals 0, then it's just x. So that's just x, which is 0. So f of x is just x, and then when x is 0, it's just 0. Okay? Then I need step 2. Limit of f of x as x approaches 0. Okay, another table. So again, I need to worry about approaching 0 here. So I need things that are slightly larger and slightly smaller. So again, 0.1, 0.01, 0.001 as I'm getting closer and closer to 0. And then the same in the other direction. Negative 0.1, negative 0.01, negative 0.001. Okay? So, according to this definition, if you're greater than or equal to 0, this side, it's the same. So this is 0.1, 0.01, 0.001. And you can see as I go this way, my limit will be 0. Okay? Now, what about the other side? So I have my thing here. This side, it's going to be 1 over x. So I am going to do a fraction, 1 over, and then I'm going to put, open parentheses, negative 0.1. Okay? This is negative 10. Now, if I change this and I add a 0 in there for this place, I'm now at negative 100. And then I put another 0 in, negative 1,000. So as I approach 0 from this way, my numbers are getting larger and larger and larger. So this is going toward infinity. And to be specific, it's a negative infinity. So this one is discontinuous because my limit does not exist. The limit of f of x. Okay, if you're ever asked this, this is does not exist. Okay, there is no limit because the two different directions are different. And if you look at this picture, I'll draw a picture for this one. This piece is coming like this way, and it's going straight down like that. And then this one starts at 0, and it's defined at 0 at a dot, and it goes just like this. And so I have a discontinuity in that place. Those lines will not meet up. All right, another example here. Looking at this problem, I need to decide if at 2 there's a discontinuity. In the future, you'll be able to look at this and say, well, this is a kind of polynomial, so it will be continuous everywhere. This is a polynomial, so it's continuous everywhere. This is part of the reason why we taught you what a polynomial was a while ago, because if you don't know what defines a polynomial, when you get here, it can be difficult. So, this is a polynomial, this is a polynomial. They are continuous everywhere. They exist everywhere. However, my question is, at this point, do the ends line up? I could end up with a picture that looks like this, okay? Or I could end up with a picture that looks like this, with a circle and a dot, and they line up, okay? And then it's defined there, and the two ends meet up. So this one would be continuous. This one would not be because they're in two different places. So I'm trying to determine, do these two lines meet up or do they not meet up? They could be like this where they don't meet up. They never meet up. But these ones, each one is a single line. So do they meet up? So, first of all, test number 1. F of C. Does f of 2 exist? Okay? Well, f of 2 at 2 is going to be this, 2 minus 2, which equals 0. So I do have f of 2. Next, criteria number 2. I need to know if the limit exists. Limit of f of x as x approaches 2. So I'm going to make my table here. Right here in the middle of my table is 2. And I'm going to do 3 that are larger and 3 that are smaller. So here's 2. What is something just larger than 2? Well, 2.1 is larger than 2. This is like $2.10. And then $2.01 gets closer to 2. Be careful, because if you did 2.11, 11 cents is actually larger than 10 cents. So this way would not work. You'd never get closer to 2. You're getting farther away. This one would be 2.001. Now, something slightly smaller than 2 would be 1.9. Notice how my numbers are close. I'm not going to go full integers away, otherwise I'm too far away to see what's happening at 2. And then, so this is like $1.90. So then I do $1.99. And then I do like the gas prices. I have $1.99 and 9/10. Okay? So this is slowly getting closer and closer to 2, and this is slowly getting closer and closer to 2. So now I need to figure out what's going on. So this one is going to be 2 minus x. Well, this 2 minus this would give me negative 0.1, negative 0.01, negative 0.001. Notice how my numbers are getting smaller and smaller. They're getting closer and closer to 0. So as I get this direction, I'm going towards 0. Okay, so next I need to check this one. Is this one actually going closer and closer to 0? So 5x plus 4. So all clear. 5 times open parentheses 1.9 close parentheses plus 4 equals, okay, that's 13.5. Then I can go into the parentheses and add a 9. That is 13.95. And then go in this parentheses and add another 9. And that's 13.995. Well, as I go this direction, these numbers are getting closer and closer to 14. Okay, because this side and this side don't match, the limit of f of x, as x goes to 2, does not exist. This is a jump continuity. And so you saw an infinite discontinuity and you saw a jump discontinuity. The picture of this at 2, this one's coming up like this. It's going to go like this. And it has a dot at 2. Okay? Meanwhile, the other one is going up right at here. We'll call this 13. And then here 14. Okay? This one's coming up like this to a circle right there. So there's a jump discontinuity there. All right. So as we're going along, there's a new theorem that I want you guys to think about. This is called the intermediate value theorem. It is very important. It will come back to haunt you multiple times, kind of like the quadratic formula. If f of x is a continuous function, so you need to know that's continuous. That means the continuity test. And a is less than b. Okay, so pick your A and B so that one's less than the other. It doesn't really matter which way, but for my writing, it's A is less than B. And there's a value n, okay, some number between f of A and f of B. Then there is a number C such that C is between A and B and f of C is n. So the easiest way to think about this is to draw a picture. So I'm going to draw a crazy kind of continuous function here. Okay? I'm going to put A here and B here. So here's B, right here. This is f of B. And then here's A right here. Right here's f of A. This is saying for some number here in between, okay, this is the number n, there is over here a value C that is between A and B, so that f of C will equal n, okay? It doesn't mean that there's only one, but there is at least one value there. Okay, there is at least one f, one C, that will give me f of C to be n, this number between. Okay, this means that you have to look at a number between the function values, and that will give you an x between your x values. Very important, and this one is so useful in predicting where zeros and polynomials are. So it turns out sometimes it's very hard to find the zeros, to find the roots. But we can guess where they are by using this theorem, and that's where a corollary comes from. A corollary means that once you have this theorem, it kind of like just follows that this comes about. It's almost an obvious way to use the theorem. So, if f of x is a continuous function, and f of A and f of B have opposite signs, okay? So this picture, I'm going to have a function that does this. And here's B, here's A, and here's B. Well, sorry. Here's A, and here's B. Here's f of A, and here's f of B. So that f of A and f of B have opposite signs, okay? They have opposite signs. Then there exists at least one value C such that C is between A and B and f of C is 0. So there is some place here where there is a 0. Okay, if f of A is different than f of B, then somewhere between there, C exists. There can be more than one, so we're going to pay attention to that, because if there's more than one, I'll show you how to see that. Now, the best way to tell if there's a 0, simply take the integers and then say there's a 0 between these two and a 0 between those two and a 0 after that. Okay? So, we are going to deal with approximating these zeros. To do this, another table. Yes, I know. This is a homework of tables. Now, I'm going to start at -3, and then I'm going to go -2, -1, 0, 1, 2, 3, 4. And I'm going to come up with what these values are. This is another reason why I said, use this calculator. So, 2 times, open parentheses, my x I'm going to start out with is -3, close parentheses squared, minus 6, all over, open parentheses, -3, close parentheses, plus 4. I do the parentheses so that I can remember what number is changing. Here I'm going to need it for the negative to let the calculator know that my negative needs to be squared. But here I didn't need the parentheses. The parentheses help me when I go back and change the numbers to change every single number I need to and not leave a negative sign when it's not supposed to be there. Equals, so this is 12, and then I can go back in here and say 2. Delete 2. This is a 1. Notice these have the same sign, so I'm not considering that there's a 0 between those. Then I need -1, -1. Now I'm at -4/3. So somewhere in here there's a 0. So between these two there's a 0. Okay? Now I need to go and put 0 in here. 0. 0, enter, -3/2. Okay, so I'm still negative. There's no possibility of a 0 between. Now I need to put a 1. And -4/5. Now this one was 1 1/3, and then this is 1 1/2, and so this went a little bit more negative. Now I'm less than 1, so this is kind of curving like this. Do you see how that's kind of curving up on me? So I'm going to expect here soon that's going to curve and give me another 0. So let's check 2. Okay, now I've got positive 1/3. Okay, the positive 1/3, that means in here there is a 0. Somewhere in here there is a 0 between those two. So remember back in Algebra 2 when I showed you how you could find all the possible zeros for a polynomial and then you had to use synthetic division to find all of them? Well, guess what? Using this method and understanding limits, you can now know that you only need to try possibilities between these two places. And it makes life a lot easier that way. All right, and next I'm going to plug 3 in. Delete 3. So 12/7, and then 4. 13/4. Okay, and so this is steadily increasing because this is just under 2, and then this is over 3, so I am still going up there, and so this is now taking off. So if you imagine this is coming down like this, and it hits a 0 there, and then it swoops through here, and it hits a 0 there, and then it's taking off. That's what's happening during this function. How about the next one, -5 to 0? So again, I'm going to set up a table. One side of this is needing to do the table. But sometimes it's easier to do a table than other things. So -5, -4, -3, -2, -1, 0. My table's bigger than what I needed. All right. So let's start by plugging in -5. 8, open parentheses, -5, close parentheses, cubed, minus 2, open parentheses, watch that because sometimes you can end up in the exponent that you don't want. Minus 2, open parentheses, -5, close parentheses, squared, minus 5, open parentheses, -5, close parentheses, minus 1, equals, so this is -1026. Okay, now I need to change everything to a 4. and I get negative 525. Change everything to a 3. And that's negative 220. Change everything to a 2. This is the long part. But it's easier to do this way than to type it all in again. Negative 63. 1. Almost done. 1. 1. Negative 6. Notice how I'm still negative and I keep increasing. Now, if all of a sudden I hit negative 63, and then over here I got negative 60, well, no, you'd expect it closer to 0. So if I had negative 6, and then I got negative 5, negative 26, negative 450, this might mean that there's a curve there, and it might have hit a 0 there. And so that would have put a question mark in my mind. Is there a 0 between those? Because, well, this is still far away. You'd want to be looking at if it's like negative 1 and negative 1 and it turns directions, or negative 1, negative 2/3 and it turns directions. 6 and 5, it's still probably far enough away that it's not going to spike on me. But if it changes directions like that and it's close to 0, then it could be an issue. Okay? So just pay attention to a change in direction. I need to go delete 0, because negative 0 is the same as 0. I'm not going to delete all my negatives. And I get negative 1. So on this interval, there is no zeros on that interval, because I'm steadily increasing, and if I continued, I might actually hit. In fact, if you put positive 1, you may actually cross that 0 line. Maybe not, but you might cross it. Okay? But on this one, there were no zeros. All right. I know this recording will be kind of long. Now we've got to discuss end behavior. So we have left hand and right hand end behavior. Left hand is going toward negative infinity and right hand is going towards positive infinity. So I'm going to try to think about this limit in the picture, and I am going to try to see what is going to happen as I get out toward infinity. Okay, as you can see here, I'm getting closer and closer to 0. I could also end up with something like this, where it looks like a parabola or something. Here, I'm getting closer and closer to infinity. So as I go toward positive infinity, I'm going to go toward infinity, where here I'm going toward a specific number. So I have two basic possibilities as I look at the end behavior. Either it's going to blow up to infinity or something, or it may go to a constant value. The other thing is, I need to decide, is it going toward positive infinity like this one, or will it do something like this and go toward negative infinity on one side and positive infinity on the other? But the right hand behavior would be as we go toward positive infinity, left hand toward negative infinity. Okay, ready to try some of these? So, for these examples, we're going to do the table here because we're going to need a table. But I also want to look at the graph, and rather than redrawing the graph, I'm going to bring the book in here and we're going to use the book. So, for these problems, let me get this situated so that you can see the book and see what I'm doing here. All right, so 4A, let's move this down. Let's see if I can get this book in here. Looking at 4A, as I go toward negative infinity, this looks like it's going to go toward negative infinity. It's going to keep going down really fast. Here, as I go toward positive infinity, as I get bigger and bigger x's, it looks like it's going to go toward positive infinity. My guess, my thought, as I'm describing its end behavior, it's going to go toward negative infinity as x goes to negative infinity, and positive infinity as x goes toward positive infinity. However, I need to describe it and then support it with numbers numerically. This means I need to write a table to show what's going to happen. So, here, I want to go toward positive infinity. Let's see if I can make this viewer here. Okay, to do this, I'm going to think a lot like before. Here's 0. And I want to pick really big numbers. So I'm going to pick things like 100, 1,000, 10,000 to find out what's going to happen as my numbers blow up. And as it goes toward negative infinity, I'm going to pick negative 100, negative 1,000, negative 10,000. Okay? Now I need to plug in numbers. My function is given here, so I'm going to type in this function, and I'm going to go, let's see, open parentheses 100 cubed, and then minus 9 times 100 plus 2. So this is here going to be 999102. Then I'm going to add a couple zeros in here. And now I've got 99959 1002. Okay, and then I'm going to add 2 more zeros in. 1 in that one, and 1 in that one equals. Now I have 9.999. Let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 1 times 10 to the 11. Okay, so that is going toward infinity. So this, as I go this direction, is going toward positive infinity. Okay, now what about going toward negative infinity? Okay, I think I'm only going to do one of these examples, even though I have 2 down, because I'm looking at my time and it's running away with me. So, negative, let's do negative there, and a negative there equals, so this is the same thing, negative 9.12345 times 10 to the 11th power. And if I remove a 0, I'm guessing I'm going to end up with the same thing in the negative. Not quite the same thing. So negative 999 0998. Okay. Delete. And this is negative 999098. All right. So as you can see, as I go toward negative infinity, I'm going to end up reaching negative infinity with my function values. All right, so that will give you 4, and I will leave this one. You can look at this one and try to do those numbers. It's the same way I did this one. But I also want to look at 5. Let me see if I can get 5 into the camera here. Okay, looking at 5, we need to describe the behavior of 5 now. Okay, use the graph to describe its end behavior and support this conjecture. So if you notice, this is 4, this is 2, and right between here is 3. And as I come up this way, I'm approaching a solid number, and it just keeps going, and it looks like it's coming to 3. And this one also looks like it's going toward 3 as I reach infinity. So now I need to support that with numbers. So I'm only going to do one of these as well. If you'd like to do the other one, you can. I'm reaching the end of what we're going to do today, but so to support this with numbers, okay, I need to do another box. Right here is going to be my 0. I'm going to have 100, 1,000, 10,000, and negative 100, negative 1,000, negative 10,000. Make my box here. All right. So now I need to plug in numbers, and my function here, I have it off screen. It's going to be a fraction, and this is 3. 3 times 100, close parentheses, minus 2, all over, open parentheses, 100, plus 1. Okay, again, I'm using the parentheses so that I know what I need to change. Let me move that up so that you can see it. Okay, equals. So this is 298. Actually, I'm going to change this to decimals. So this is 2.9504, repeating. Okay, so now I'm going to change these to 1,000s by adding a 0. And now I have 2.995004 repeating. And then I'm going to add one more 0 here. Zero. And now, oops, okay. 2.99950005. Okay, notice how I'm 2.95, 2.995, 2.9995. This, as I'm going this direction, is getting closer and closer to 3. Okay, so I've supported that way toward positive infinity is 3. Now I have to do the same with negative infinity. So I'm going to throw negative signs in here. Negative. And I want this. This is 3.0005, and that's repeating. Take away a 0 here. And this is 3.005, and that's repeating. Delete another 0. And this is 3.05. Okay, this is $3.05, $3.05 of a cent. This is $3.05 of a cent. As I am going this way, I am getting closer and closer to 3. So the limit, the right-hand end behavior is 3. The limit as x goes to infinity is 3. And the limit as x goes toward negative infinity is also 3. All right, I promise I won't be too much longer. I know I'm using up a lot of your time. But sometimes we don't have a graph, okay? We have to read through this. So I'm going to look at this and try to think about the end behavior. I'm looking at this thing here. And since I'm doing end behavior, I'm going to end up making a table. But remember how I told you when you see something that's a fraction like this, it's usually in that shape, kind of like this. In fact, this is the graph of 1 over x. So I'm going to guess that this is going to go toward a number from both directions. but this is also squared on the bottom, and it's 8, and I don't know. So I am going to draw my thing here, and I'm going to have 100, 1,000, and 10,000, negative 100, negative 1,000, negative 10,000. And now I need to plug in these numbers so that I can find out what the behavior is doing without looking at a graph. Because you have to first look at a graph when you're starting out, but as you move forward, you don't need to be looking at a graph anymore. All right. Looking here, we're going to have, let me move that into your sight so you can see what I'm doing. A fraction, 0.8, and on the bottom, I am going to put my 100. Open parentheses, 100, close parentheses, squared. Okay, that's 8 to the negative 5. 8 times 10 to the negative 5. And then I'm going to add a 0 in there. 0. 8 times 10 to the negative 7. And I'm going to add one more 0. 8 times 10 to the negative 9. Remember, the negative is going to move my decimal, this one 9 places this way, 7 places this way, and 5 places this way. So as I get farther and farther this way, I'm getting closer and closer to 0. Now, what about the other side? Let's stick a negative. And you can see I'm actually getting the same value. It's going to be the same value because negative times negative is the positive, and it's the same as squaring the positive version. So this one is the same as before, and I'm going to get 8 times 10 to the negative 7, 8 times 10 to the negative 5, and again, as I'm going this way, I'm getting closer and closer to 0. To give you an idea of what we have going on here, this is 0.8, but it's coming down along this way, getting closer and closer to 0, and coming down along this way, getting closer and closer to 0. All right, this one I'm going to leave for you guys if you would like to try it. It's the other example under, well, it's another problem that's in the book. This is your homework. Today you do not have Alex's homework. Your homework is 1, 3, 9, 11, 13, 19, 21, 25, 27, 29, 33, and 35. You have a paper homework, so you will need to complete this and turn this in to your teacher so that they can scan it and send it to me to grade. All right, enjoy your day.